Okay, in this video lecture, we're going to talk more about rational functions and their key features, and then using their key features to come up with a reasonable sketch of even some more complex functions. So we're going to start by working through this warm-up problem where you're going to find all the holes, x-intercepts, and vertical asymptotes, which is all we've covered so far. And then just for a quick review, write the domain of the function. So you should pause the video and try to do this by yourself, and then I will work through it when you unpause. Okay, so we were looking for x-intercepts, vertical asymptotes, and holes. And the first issue is that this function is not factored in the numerator and denominator, so we should try to factor first. So in this numerator, we can see that we can factor out a common denominator, or sorry, a common factor. So we have, oops, that's not what I meant to do. Okay, so we can factor out an x, which gives us x squared minus 6x minus 27, right? And then we can further factor that other piece. So we have x minus 2 times x minus 9 times x plus 3. So now this is fully factored. And then now we can factor this denominator. We have x already, and then we have x plus 11 times x minus 2, right? So now this is our fully factored function. I'm just going to go ahead and rewrite it. So in general, let's put the x out front. I feel like that makes it look a little neater, and then we'll also be able to see things a little bit more clearly. So we have x times x minus 2 times x minus 9 times x plus 3, and then that's divided by x times x plus 1 times x minus 2, and then times, that's it. Okay, cool. So those are our factors. So then let's kind of code these. We see we have a matching factor in x in the numerator and denominator. Okay, we also see we have an x minus 2 and an x minus 2. And then x plus 1 is only in the denominator. And then we have x minus 9 and x plus 3 only in the numerator. Okay, yeah, and then this is 11, x plus 11, not x plus 1. Okay. So let's start to deconstruct this and figure out where our key features are. So we know that we have an x-intercept whenever we see a factor that's only in the numerator, because this is going to give us an output of 0, right? If we do 0 divided by a non-zero number, that gives us an output of 0, which would output of 0 means we are on the x-axis because we're not traveling vertically at all. So we have one at x equals 9 and one at x equals negative 3. All right, and then we have a vertical asymptote. VA is when we're dividing a non-zero number by 0, dividing by 0. That's covered in another video lecture. And that's happening at x equals negative 11. All right, and then finally we have a couple holes. We have one that should be happening at x equals 0 because we have an x, and then we should have another one that's happening at x equals 2. So then to find the y value of these holes, we have to plug in these x values with those common factors canceled out. Because if we try to plug in x equals 0 right now, we're going to get 0 over 0, which is why we have a hole. If we tried to plug in x equals 2, same idea. So we should cancel those factors and now plug in x equals 0 to figure out the y value there, and then x equals 2. So first, when we plug in 0, we're going to get negative 9 plus 3 on top. And then on bottom, we're going to get 11 because we're just replacing all the x's with 0. So that's negative 27 over 11. Let's just go ahead and leave it like that as that fraction. Now what happens when we plug in x equals 2? We get 2 minus 9 times 2 plus 3 over 2 plus 11. So that's negative 7 times 5 on top, and then 13 on bottom. So that's negative 35 over 13. Again, we'll just leave it like that. All right, so there's all of our key features. We have our x-intercepts, our vertical asymptotes, and our holes. Let's look at a quick graph just for context. So we have our hole at x equals 0. We have our hole at x equals 2. We have our two x-intercepts, and we have our vertical asymptote at x equals 11. You can see how all these key features show up on the graph. All right, all of those key features we found. For another review problem, we're going to look at this table for a polynomial. This was a struggle in the Desmos activity, so I want to make sure this goes okay. So the first thing we see is we have a positive start and a negative end, which is another way of saying that we have an end behavior of up, down. Because they're differing, that must mean we have an odd degree. Just important to note because we're going up, down. Okay, the intervals tell us kind of where our x-intercepts are. So we're split up by x equals -5, x equals 0, x equals 3. So that means that we must have an x plus 5 factor to create that x-intercept at -5, an x factor to create that x-intercept at x equals 0, and then x minus 3. Okay, the next thing to see is that we're positive and we stay positive, which implies that we must bounce at this -5, which means that this must be an even multiplicity to make that bounce, to go positive, positive. Okay, and then we cross at x equals 0, so we can just keep that as a multiplicity that's 1. But then we bounce again at -3, which means this must be even. And if we add these up, we get 2 plus 1 plus 2 is 5. So we currently have a degree 5. That's good. Now the only adjustment we did make is that normally an odd degree has an end behavior of up, down. So we have to throw a negative out front to make sure it's going to go, or I meant normally it would be down, up. So then we want to make it up, down by throwing a negative out front. So this function will work nicely for this table. So now we need one more key feature that we're going to examine that's going to help us sketch. We're going to start by thinking about just what happens when x becomes really large. So what's going to happen to this output? We plug in a really big number. Let's say we want to plug in 1,000,000. Okay, so you can probably see right away what this is going to approach, but think about it like this. If we have one cookie, and we try to divide that cookie up into 1,000,000 pieces, right, and give it to 1,000,000 people, how much does everybody get? Well, we're dividing 1 by 1,000,000, right? So everybody gets basically nothing. So this is basically equal to 0, and as x gets bigger and bigger and bigger, this is going to get closer to 0. And it doesn't matter if we start with 5 on top and divide it by a big number, or 10, or even 1,000, because even if we do 1,000 divided by a really big number, the bigger it gets, the bottom compared to the top, the closer we're going to get to 0, right? Even if we start with 1,000,000 on top, that's a big number, relatively, but if we do an even larger number on bottom, then we're going to get an output that's close to 0. So the idea here is that as x goes to infinity, then f of x must be approaching 0, right? As x becomes bigger, the output's going to get smaller. That's all this is saying. So we can look at the graph, right? And we can see that there's this the graph is approaching 0, right? And then even if we go to 1,000, right? X equals 1,000, we can see if we zoom in enough, really it's not quite equal to 0. It's really close, but it's just kind of slowly approaching 0. So even though if we look at this picture, it looks like the purple line just kind of goes on top of the dotted line, what's really happening is that the purple line is just getting infinitely close to that dotted line at x equals, or at y equals 0. But this is like a simple rational function where we just have like a normal number on top and a variable on bottom. But the question becomes, what if we want to take a function with variables divided by another function, right? So it all comes down to comparing the size of these functions. So what you should do is go to this URL, and I want you to order these functions in terms of which one do you think is going to become largest, meaning largest output, compared to which one will be smallest relative to the others. So look at these 6 functions, and just put them in order. Pause the video while you do this. Go to this link. You'll be going to a Desmos activity to do this. And then when you're done ordering, you can come back to the video. Okay, so hopefully you tried to order those. And now we're going to look at what happens when we plug in big numbers to functions like this. So I plugged in 1 billion to these different functions. And you can see that x to the 5th minus 2 is relatively way larger than the other two. And if you want to look at the other two, the 4x to the 4th versus 3x to the 4th, they are the same size in terms of numbers of digits. We just have the 4 out front instead of the 3 out front. Now we have the x squared plus 2. We have the 2x squared plus 15. But I'm showing you color code wise how that affects the function. So if we just did the 4x to the 4th plus 2, we would get this thing. Adding an x squared just changes that number. Adding in 2x squared just changes this number. So what happens is that these pieces end up becoming super irrelevant when x becomes really big. What it really comes down to is just the variable with the biggest exponent, the degree, right? So this minus 2 does not really matter when x becomes big. All right, and if we divide these numbers to compare their size, we're going to see that the fact that this is so many more digits is going to make an output really small if we divide the blue by the red. So we'll try that really quick. I'm just going to do it. I'm just going to write, what if I do the blue divided by the red? And it ends up being like, okay, it's like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, right? It's basically this, 0.00000000, maybe 4, but it doesn't really matter, right? Because this is really just equal to 0 if we try to divide the blue function by the red function. So if we take 4x to the fourth plus x squared plus 2 divided by x to the fifth minus 2, what's this going to approach as x goes to infinity? Well, it's just going to approach 0. Because the bottom is going to become so much bigger than the top, so when we divide them, we're going to end up with an output close to 0. So what if we do blue divided by yellow? Well, we can see that they're the same number of digits, right? They're basically the same size, and basically what ends up happening when we plug in a really big number is that those big numbers cancel each other out, and we're just left with the coefficients. So at infinity, again, I kind of talked about this already, these pieces don't really matter at all because they're so small compared to 4x to the fourth and 3x to the fourth. So they're negligible and we can basically pretend they're not there. So then we're just left with 4x to the fourth over 3x to the fourth, and then since we have an x to the fourth over x to the fourth, we can now just cancel those, and we're just left with 4/3. So at infinity, since basically this whole function cancels out except for the 4 and the 3, we're just going to approach 4/3. So this is the idea with rational functions. When we divide a couple functions, right, one function in the numerator, one function in the denominator, what we really end up with is a horizontal asymptote in some cases. And this is what you can think of as the end behavior for rational functions. With polynomials, yeah, the function is going to end up like pointing up and up or down and up, whatever. With rational functions, that's not always the case. It's all about what it approaches at infinity. So when you think about end behavior for rational functions, you really should be thinking about horizontal asymptotes. And these are the 3 cases now, and you should pause the video and write all 3 of these cases down. We've already justified what's going on here and what's going on here, right? Again, at infinity, these other pieces aren't going to matter because 10x cubed is way bigger compared to the rest of them, and x to the fifth is way bigger compared to the rest of them, right? But now we're comparing x cubed over x to the fifth. X to the fifth is going to become way bigger, which means that when we divide these, we get 0, okay? Again, cancel these. They don't matter at infinity. They're too small to matter, right? And then we're just left with x to the fifth over x to the fifth. Those cancel, and we're just left with 2/3, whatever these two numbers are. Okay, if there's a large degree on top, that means that the numerator is going to become way bigger compared to the denominator. So when we divide them, it's just going to end up with a big number. So there's going to be no horizontal asymptote when there's a large degree over a small degree. And these are our 3 cases always for rational functions. So hopefully you've copied those 3 down and you're now unpausing the video to continue. So here's just a few examples. Okay, you can see here we have a large degree 5 over a small degree 3. These are actually the examples from the previous slide. Okay, so you can see there's no horizontal asymptote. It's not approaching anything in particular. It's just going up to infinity this way and down to negative infinity this way, not approaching any kind of value. But then here we can see it's a small degree over a bigger degree, and we're approaching 0, right? A horizontal asymptote at y equals 0. And then here, they're matching, and then we have a 2 out front versus a 3 out front. So then we're going to approach 2/3 as x goes to infinity, and you can see that we're approaching 2/3. Okay, as x becomes bigger, we get closer to that 2/3 line. So here's a few practice problems you can try. Pause the video, try to determine the horizontal asymptote, unpause for answers. So for this top one, we have a horizontal asymptote at negative 5/7 because we have a degree 5 over a degree 5. So we're going to just pull these out front. And then we have a degree 9 over a degree 11. So the degree is bigger on bottom, meaning we're going to approach 0. Now with this one, we have to determine the degree by looking at factored form. So let's see, we have a degree 3, 1, 2, 3 over degree 3. So again, that's the same degree, meaning we're just going to approach whatever these leading coefficients are as a fraction. So it's going to be y equals 6 over 2, which is equal to 3. So again, in factor form, you have to determine the degree by looking at the number of factors. So in this case, we have a degree 2 divided by a degree 3. So in this one, we would approach y equals 0 because the degree is bigger on bottom. But then in this one, we have a degree 3 because there's 3 factors over a degree 3, right? And so that's going to approach y equals 4. So think about it this way. If we're plugging in a really big number, we're plugging in infinity. Infinity minus 2 is basically the same as infinity, right? Because we're just taking 2 away from an infinitely big number. So pretend that this minus 2 isn't here, only at infinity. Okay, pretend this minus 5 is not there at infinity. Okay, infinity plus 7 is pretty much the same as infinity minus 5 because it's just a big number plus a really tiny number compared to a big number minus a really tiny number, right? X plus 2, it's all the same. So really what we have is we just have 4 times x over x times x times x, right? At infinity only. And then, so we can cancel these x's, so we're just left with 4 over x, and then it turns out that 4 divided by infinity is going to be equal to 0, right? So that's just another way you can think about these horizontal asymptotes if you're in factored form, is that all the factors are pretty much the same because we're just subtracting or adding some kind of finite small number to infinity, which is not going to make a difference. So we're really just left with the x's, which will cancel each other out.